Welcome to an introduction of Halo Seals. This training is going to cover the operation of the seal, tell you a little bit about how they work, where we use the seal, the value the customer will see, and what it brings to the table in terms of what the customers get from the seal. We'll talk a little bit about our experience, but as it relates to centrifugal compressors. The seals are also available for gas turbines and steam turbines, but this training focuses primarily on compressors. Centrifugal compressors have evolved over time, much like all of our equipment. This table shows from the 1950s through pretty much today how the efficiency of the units has improved. And it really is for a number of reasons. Our legacy units back in the 50s were designed using slide rules. Our forefathers didn't have computers, and they had to spend an awful lot of time developing. Many engineers would calculate the few things that they did to come up with the performance of the stage. Then they would test them, put them through development, and build a multi-stage test vehicle. And sometimes they were not at the peak and most efficient point on the map. Over a period of time, as we developed better softwares, we got computational fluid dynamics and finite element analysis to evaluate stresses and mechanical attributes. The softwares and the even spreadsheets, all the abilities that we have with computers, that alone has made it much easier for us to optimize compressors. And really, the design of compressors was in its infancy as well. I mean, if you go back a decade ago, it was the first time we built a compressor. So as we learned an awful lot, and through the 80s and 90s, the software really made a transitional difference in terms of compressor design and selection. We have ingrown software and tools that allows us to optimize stages as well. It was in the late 90s or in the late 80s and 90s that we started scaling and using contour trims to select a stage and an impeller to be exactly on top of the design point and optimize every single blade passage or blade and vane in the stage and the passage as well, the diffusers and return channels. Alongside the improvements we've made on software and capabilities, we've also built upon our experiences. Just the design process itself, where you test and bring the knowledge back and put that into the design process, that has also helped. Years and years of experience in each industry and each service and each type of compressor has made us better. And in parallel, many improvements in manufacturing processes, 5-axis milling machines and fabricated internals. When we start this curve in the 50s and 60s, we had riveted impellers. The rivets were in the flow passage, creating turbulence and disturbing what we were trying to do inside the compressor. Cast internals. The diaphragms and internal components were often cast, or almost always cast, and those had porous and rough surface finishes. That led to additional losses in the flow passage. So today we make fully fabricated. We've even gone to the length of honing, and polishing the surface finishes to get that last 0.5% of efficiency out of the stage. So this graph does say additional gain to stage design will be expensive. What that means is there's no more low-hanging fruit, so to speak. The things that we could change very easily at a low cost perspective have been changed. Today, if we want to further close the gap between what Mother Nature will allow and where we are with centrifugal compressors, we're going to spend a great deal of process time and energy, development testing to find that last further optimization in the stages. And that's not to say that every compressor reaches 89% efficiency. Certainly it doesn't. But this is in general in general, the trend of efficiencies in the industry. Um, the one aspect that I haven't mentioned is internal labyrinth seals. So when a compressor does its job and builds pressure, and there's a pressure differential between a rotating part and a stationary part, there's going to be motivation for gas to move from high pressure to low pressure. And we use aluminum labyrinth seals internally at locations like impeller eyes and between the stages, between the impellers, or at a balanced drum to stop that flow of gas. You know, at the very beginning, 100 years ago, the best thing we had was taking a chunk of aluminum, putting some teeth in it, much like the picture here. Sometimes we call them knife edge aluminum labyrinths, sometimes we call them tooth labbies. But whatever the material and whatever the shape, it was take that chunk of aluminum, stick it into the compressor with as tight a clearance as possible, and hope that it stays. And here are some additional changes and improvements we've made to the aluminum labby over the years. So we've changed its material, we've changed its shapes, we've went from polymer materials to you know, bronzes and nickels, depending on the service and depending on the corrosive nature of the gas. We've tried rotating labbies, we've tried stationary labbies, we've mixed it in with all kinds of different devices, and you can see the varied changes that we've made to these seals over time. And they really have come a long way, you know, in terms of how well they seal and how long they last. This seal here is the current standard for the Siemens STC new equipment compressors. And the blue piece, the labby piece, the labyrinth piece, would be made of a steel, so that the wear on those teeth would be minimized. The teeth themselves ride on the rotating component. This is the portion of the impeller that we call the eye. So this is the impeller eye. It's stepped we found that when we step labby teeth, it makes a more tortuous path, and that further reduces leakage. And they went one step further. They're putting an abradable material onto the rotating surface and designing these teeth to basically be metal to metal, to come in contact with the impeller or rotating surface during the design or at design pressures. And it's a great seal. The leakage is very good compared to a straight bore aluminum labby with a high level of clearance trying to not contact at all. The thing is, between all of the seals that I pictured, and some of them went by very quickly, I understand, but all of those seals, those conventional seals, no matter what the design or how it works, they all have one thing in common, and is that they wear. There will be contact at some point in time during a process upset, during first criticals, as you get to overload or high speeds and you come close to the second criticals with the machinery. There are things that create vibrations, cross-coupled stiffnesses and forces on the rotor that make vibrations come about. Sometimes through the life of the machine, sometimes just periodically, just in a few moments. But a mechanical seal like this that touches off, they're going to wear, and the net clearance is no longer per design, and you will get higher leakage from that seal. Well, I'm happy to report that there is now a solution for this, and it is what we call the halo seal. The halo seal is a dynamic, pressure-activated, non-contacting stationary seal designed to provide optimum performance with a tight sealing clearance. In addition to reducing recirculation losses and saving power, the dynamic nature of halo seals allows it to be tolerant of rotor seal offset, rotor runout, eccentricities, centrifugal growth like at impeller eyes, and vibration. Halo seals maintain design clearances throughout the operational life cycle of the machine, drastically reducing hydraulic performance degradation between scheduled maintaining efficiency, and it maximizes production and reduces maintenance costs. That's a mouthful. That's an awful lot of things to state. But let me just break this down a little bit easier. So this is a picture of the seal, and you can see there's segmented ring here with what we call pads. Those pads are installed with a large clearance to the rotating surface. So if you can imagine in this picture, the rotating, let's say shaft, would be here on the inside. As you build pressure across the machine, okay, you turn the machine on, it starts to rotate, you're going to build some pressure. As the pressure builds across that seal, those pads will draw toward the rotating surface and what we call activate. It'll activate the pads. All it means is they're going to draw closer to the surface. They're going to end up at a tight running clearance. They're designed to. But the seal itself is dynamic, and they're going to move away from the rotor as vibration or any of these other things occur. So that's why we call it dynamic. Now, the other 2 points here is that the halo seal itself, because it has some spring features in there, is made of Inconel material for infinite fatigue life. The seal is made to directly replace conventional seals in no matter the location they're at. This is the cross-section of the halo ring itself, the ring inside the seal. And you can see this is the pad here, and there's that segment. You could see it in the last picture. It is held to the fixed ring using these springs or beams in this feature right here. That allows the pad to move up or down in this picture. Now there's some physical stops on this as well, and that's primarily to save the seal from handling. Not really part of the function of the seal when it's in operation, but as you press it, we love to push the pads in and out, or as you assemble the compressor, we certainly don't want the seal to be damaged during those periods. This is back to that other cross section. So this is the ring, the fixed ring with the springs and the pad here in the blue. There is a front plate in green and a back plate in red. And front and back just means that the front is on the high pressure side in this case. So the high pressure would be on the left, and the low pressure, the downstream side, would be the red, the back plate, or on the right. There is also a mid plate in the middle and some secondary seals. If you can't tell which plate is front or back from looking at the seal, look for the secondary seals. These little purple in my picture. Those seals push against the mid plate and the pad, and they'll accommodate pad motion, but this would be where the high pressure pushes those secondary seals into the primary pads, and it'll keep gas from going through the seal itself. So the only way the gas can pass this seal is to go between the pad and the rotating surface. Okay? Now, we're going to talk about activation. So how you activate a seal, and here's a CFD analysis of the pad. This is the same cross section. See those 3 teeth here? There's 3 teeth, and then this pad over here. So here's the pad, and this is the space between the pad and the rotor. So this black line would be the rotor. So if we just build 16 pounds on this particular example, okay, it's not always 16 pounds, but in this example it's 16, and we're going to seal against atmospheric pressure, and this seal was located at 20,000. So this would be typical of a install clearance. And the way you do this program analysis with the CFDs, you have to put the pad in place somewhere. So if it were 20 thousandths install clearance to the rotor, this force would create a negative pressure. The Bernoulli's equation. It's like the wing of an airplane. Think of that. And as the flow passes underneath the pad, it's going to create a negative static pressure. And the summation of forces on this pad is going to push the pad down to the rotor. And on the other end, if the rotor was very, very close to the pad, let's say 2 thousandths, the summation of forces, where this is all red now, it's all 16 pounds, there is no negative pressure behind it. This would force the pad up. So it'll find its happy medium where all the forces acting on the pad summate to 0, and the pad will stay. So when we talk about activating, It means that as you put pressure underneath there, or pressure across the seal, and flow passes underneath it, it creates a negative pressure, and then the pad moves down to find its natural force balance. We're going to design the seal so that at the design operation, like guarantee point, we're going to be in the neighborhood of maybe 4 thousandths, 3 thousandths to 5 thousandths clearance. And that's going to be pretty tight. In some cases, tighter than an aluminum labby, maybe even quite a bit tighter than an aluminum labby can achieve. So it'll result in low leakage. And they're dynamic because if the rotor starts to move up, the forces are going to act and keep the pad in a position related to the rotor. So it's dynamically stable. And that also means that across the compressor map, we're not going to have the seal deactivate or lose its clearance completely. It's never going to just spring back to its installed clearance while there's force across the pad or flow underneath the pad. So we also say because of that, it's non-contacting. This is a graph that depicts 3 types of seals. First, in red, is the conventional aluminum labyrinth. The second is the polymer labyrinth. Because that's a pretty popular replacement, we have Peak and Torlon available in the industry, and then Dresser-Rand made its own proprietary mix we call DR13HT material, but it's basically a PEK material. And then the third is the halo seals. Okay, so what I say here is that the aluminum and the polymers still wear, right? The aluminum wears completely, the polymer still wears a little bit, but the halos do not wear. Okay, that's a big claim, but the seal, this isn't a perfect example here. The seal would be installed with a large clearance where the aluminum would be at a low clearance, and the polymer would be just a little bit above that due to thermal growth and the dynamic nature of polymers. They can actually grow a little bit differently than the steel, so they need to be installed with a little bit larger clearance. If you pass through a startup, for instance, as you start the machine up, you'll eventually get to the point where there's enough pressure that the halo seal activates. The labby or the polymer really won't change much. But as you go through that critical and there's a vibration event, those seal diameters, I say seal diameter, okay, but think of it also as clearance. They're gonna get opened up because the rotor will have vibrated or moved, and the seal diameter increases. Now aluminum, every time you touch it, is going to not come back. There's going to be no springing back to its original shape. So if you touch and there's a first critical event, or through normal wear and tear, it's gonna erode out a little bit. Or if you have a very heavy surge event and you achieve even higher vibrations, you're going to continue to increase the diameter of that seal and therefore increase the clearance to the rotating piece. The polymers are known to have a little bit more resilience, and they're going to snap back. So if you go through startup, we are hoping that they stay nearly design, if not exactly on design. But if you have a first critical and you touch them, they will wear. They can wear out significantly, and you can melt the polymer right out of your machine if you have a very heavy or major extended event. So that's why I end the polymer labby and the aluminum labby kind of at the same piece, and just kind of separate them here so that you can envision that they're both in there. The halo seal, even through a major extended event, is going to excite. It's going to see a lot of motion, and the rotor's going to be banging around and vibrating, but it's not going to contact. It's got the ability to push those pads out of the way a great deal, and then come back. Now, I show this a little bit higher because no one's done any testing on this, but you can envision that the halo seal, you can break anything, so I show it a little bit, but if it does what it's intended to do and the way we've designed it and the way we've seen it in operation to date, the halo seal is going to be doing very good and maintain that performance of that machine even through some fairly severe events. There are 3 value propositions to the halo seal, 3 pillars, if you will. The reduction in horsepower consumption. So this is hydraulic performance. It's going to improve that performance. That means higher production rates. That means lower cost of ownership. That means it costs less to run the machine, higher efficiencies. The second pillar is increased reliability, or low maintenance costs. So if you're gonna run this machine longer between outages, you're gonna start saving some money on those outages, and you're also gonna produce more gas, so that makes more money too. So increased reliability and lower maintenance. The third pillar is a soft benefit. We are only going to offer halos at this time where they can be completely interchangeable with labyrinth seals. So if you have a machine that currently has labbies and you'd like to put halos in it, no matter the manufacturer, they can be put in. But we're going to look for the physical space to ensure that the seal fits in that space. If it requires modification and we're not modifying the machine, then we will let you know and we will not offer the halo. But in the case of, let's say, a revamp where you're going to modify those internals, that gives us the ability to put the halo in and make the physical space that it takes up to accommodate, and then we can make a labby to take its place. The key here is that a customer will never be left stranded with a unique, highly advanced seal that if something goes wrong or if they don't like it for any reason, that they can't get rid of it. Because an aluminum labby, a conventional seal, may not be able to meet the same performance as a halo. So we want to make sure that there's never any problems with the seal. Okay, and if there is any reason to take it out, that you can do so without harm. Now, I like this picture. This is one of our very first compressor installs. It was a new equipment unit. We did factory type 1 and type 2 testing on it with and without halos. So we did conventional labby seals in a J-hook style and in a dovetail style arrangement. There's the halo on the right hand side in the same two spots. Obviously different shapes, and you can see it's a little hard, but there is that fixed ring, springs, and beam, and down here fixed ring, springs, and beam. And you can see that the halos can fit into a fairly compact space when they need to be. But this shows both configurations, that they're completely interchangeable. And in that factory test, we were able to show the hydraulic performance difference using the Type 2, and the Type 1 at full pressures, we were able to show some mechanical attributes of the seal. This is a picture of some photos of the seals in the most useful location in a compressor. In the left, it's at a division wall of a back-to-back compressor where we needed a damper seal at the division wall for rotodynamic reasons. You can see the swirl brakes or the flow straighteners on this. The high pressure end is at the top, and it comes through the hole pattern seal, which is made of aluminum, if you're not familiar with that. And then it enters the halo seal and goes through that at the end of the division wall to this would be the first section end. When utilizing this with the hole pattern, we call it a hybrid seal. So this is a hybrid hole pattern halo seal. The halo serves to reduce the leakage a great deal. Now, those of you who know what a hole pattern seal is, you know that it needs the leakage to be effective. It needs a pressure differential and a lot of flow. The thing is that we've gotten very good at predicting the damping coefficients and stiffness of these seals, and in certain rotors, we don't need that full amount that the seal can provide. So in that case, we can design the halo to reduce the flow as much as possible while still providing the rotodynamic requirements in the seal. On the other side, on the right side, is a balance piston halo seal, and you can see that we use two halos separated by a gap, and this took the place of many labyrinth teeth, about 18 on this compressor. And we just wanted to show you that two seals could be utilized. We could use 3 seals, but we do a cost-benefit analysis to determine if adding a third seal or a fourth seal to a location would provide enough horsepower savings to justify the cost of adding another seal. Okay, So that's something that we can do for your machines as well. But both of these seals have very high, the full pressure across them, so they're usually very beneficial to look at halos. Now for some examples. I'm going to show you two machines first, and it's for syngas service, so low pressure and high pressure 2B Dresser-Clark legacy compressors, designed in 1985, revamped with what we call some people call it the super barrel lineup, and 1, 2, 3, 4. This is like an 8-stage unit straight through. The low pressure compressor and the high pressure are both straight throughs. We can utilize the halos here at the impeller eye seals, all circled in blue. The interstage locations circled in red. I put 0 horsepower differential here because sometimes across the map flow comes right to left through the seals and sometimes left to right. The idea that the amount of flow through that seal is somewhat negligible. It's low in almost the entire map, and so reducing that leakage, to get a consistent approach across the entire map is pretty low. So we just say basically we're going to treat that as negligible in terms of hydraulic performance. Okay, so that's just going to be zeroed out. And then the magenta, or this purpley color, that's your balance piston. And this cavity behind the balance piston would be balanced all the way back to the suction side of this machine. So it sees the full pressure of all the stages, 8 stages. And so for one halo seal, in this case, that's there's the swirl brakes and a hole pattern. This is a hole pattern seal. In this case, you would replace it with a hybrid hole pattern halo seal, and you could save 26 horsepower out of 10,000. So not the best payback, in this machine, but it's a low pressure machine. Okay, and on the impeller eyes, we can save 70 horsepower. And again, the payback here, because you'd have 8 seals at a higher cost, is only 7 years payback. Or I shouldn't say only, it's 7 years, which is not very good. But if you look at the high pressure unit, same arrangement. We've got the recycle section down here. We've got, I think, 8 seals. Yep, 8 impellers again. We've zeroed out the interstage seals. And the high pressure balance piston, which is also hole pattern, we can save 152 horsepower out of 10,000. So it's a much better savings than the low pressure unit and a much better payback. Now, one thing I will point out on both of these compressors, since this is balanced back to the inlet, the interstage or gas balance seals, which are here and here on the machine, at each end, those aren't even evaluated on straight through units because it's assumed to have zero flow, nearly zero flow across the entire operation of the unit. So here's a summary of those two units, and the table just gives you some indicators, right? So horsepower savings is a certain indicator that would tell you if it's going to have any value. So we've put those here for the impeller eyes, the balance piston, and the interstage. And you can see there's the zeros. So 70 and 26 from the LP, and 128 and 152 for the HP. This is the percent efficiency gain in relation to each unit. So 70 out of, I forget what it was, but it's 0.7 of a point. So we're saving on this unit at design clearances, comparing traditional aluminum labbies to Halo, we're saving 376 horsepower on those two units, roughly 2% efficiency gain. This is the pounds per minute reduction on all the seals. It doesn't mean as much to most people, unless you're a process guy specifically looking at that unit. But this is the payback with our calculation. So we're getting to just 3 years payback on full set of halos. Now that's all in the red. What I'd like to talk to you a little bit about is the blue side. And as seals wear, we talked about those events, the startup, first critical, surge events. As those events happen, you're going to touch off the seals, and they're going to wear. I mean, they are called wearable parts, so they're going to wear. And when we take compressors apart, we often see an excessive amount of wear on those parts. Well, our recommendation at Dresser Rand, at least, was that if they get to 1.5 times the design clearance. So let's say if a seal was a 10-inch seal and our design clearance was 10 thousandths, 0.01 inch for that seal. If it achieved 15 thousandths or 0.015, you would replace that seal. Now, if I look at a comparative analysis of halo to aluminum labbies that are at 1.5 times the design clearance, look at how much more benefit we have in terms of horsepower savings. It goes up over 2 quite a bit on these machines. Sometimes it goes up quite significantly. And in this case, we're getting almost 5% gain on a 20,000 horsepower train. So its payback drops almost to a year payback. And if you look at specific seals, like this balance piston seal, it's measured in just mere months. So it becomes much more valued in terms of hydraulic performance. There's still the mechanical performance, there's still the extending the life of the unit's benefit. Here's another example, and this time it's a back-to-back compressor. This is for gas export. It's a Datum 14, so it's a more modern machine, radially split, 7 stages. So here's the first section of compression with 3 impellers facing. This is the inlet. Here's the discharge. The gas goes and gets cooled and returned to the compressor here on this end through these 4 stages and then out to the process. Okay, so this would be the discharge. Sorry, I'm not showing the case. It's a little confusing, but in this case, you still have the blue locations, the impeller eyes, and you have the red locations, the inner stage or the between the impeller locations. And I don't even show the red down in the summary because we assume it to be negligible. I've added to this one the end seals, the gas balance seals, because here in the orange you can see they're very long, but this gas leaves the inlet and gets piped over to this side of the machine and comes in. This is lower pressure than this side. So the orange seal, it recirculates around the first section of compression, these 3 wheels. The green seal, which is the division wall, okay, that gas leaves this last stage. It comes through the seal, out the flange, through the cooler, and into this section of compression, and it recirculates around the second section. So even though they circulate only around one section of compression, they are big candidates for improving the recirculation and the waste inside of a compressor. The impeller eye locations, 7 in total, will save 239 horsepower. The division wall will save 288 horsepower, and the end seals can save 55 horsepower in relation to the design point comparison of traditional aluminum labbie seals in a 51,000 horsepower unit. And these seals are designed well. If you look at them, there's 6 teeth, I think, on these impellers. A lot of our legacy units only have 3 teeth here. And if they have a large clearance as well, you can save quite a bit just by improving that seal or moving them to halo and really improving the leakage. In this case, and in many back-to-back configuration machines, the division wall has to be a damper seal, something that you need for rotor dynamics. And as we showed in that photo, you would put a halo seal in replace of this labyrinth seal right here. Okay, now there's a shunt hole. This is returning gas from a higher, this is taking gas from up here at the top, and it's injecting gas here. We have new designs for that. So we would inject the gas out front to deswirl it, and this place would, this area would be where we'd put the halo seal. Okay, so it would take very little cost to put a halo seal into this machine. That's why the payback is so good. The cost is lower, and the payback is measured in just months. Now, when we look at the blue side of this table and we start to increase the clearance of those traditional labbies to 1.5 times the design clearance, the payback is just significant. 1,263 horsepower savings. It's over 2% of the unit on a 50,000 horsepower unit. The payback on that division wall is now measured in weeks. Overall, you can retrofit this machine with halos and have less than a year payback. So at this point, most people are, filled with these details, but they're still questioning where did halos come from, and is it ready for the open market? Is it ready to be sold to my customer or offered on my machine? And this is a slide that just gives a little bit of the background. I could give an entire presentation on where these came from and who invented them and how they got into our industry. Okay, but the basics are that a company called ATGI, they developed this really for the gas turbine flight engine market. They were working with the U.S. government on creating the most efficient seal possible. And so for many, many years, so 10 years in development, they worked on this. It wasn't until 2012, and it wasn't until they had years and years of experience in the gas turbine market space that they came to the oil and gas industry. And in 2012, they put it into the first centrifugal compressor, and in 2014, they put halos into their first multi-stage steam turbine. It happened to be the same customer, okay? That customer, and I'm speaking in terms of the centrifugal compressor now. That customer had a compressor that was a bad actor. It was really having a hard time with reliability, with availability. They were having shutdowns every 3 to 6 months because they would go through process upsets and surge events, and they claimed that they could watch the efficiency of the unit step down in a very, very fast manner. So they worked with the original equipment manufacturer, and ATGI joined the efforts. They did a few changes to the rotor, and ATGI retrofitted the machine with halos. And that machine, in September of 2017, just passed its 5-year run with a scheduled outage. That's the first time they had gotten that machine to 5 years. They came to that outage. The efficiency had not decreased. There was no evidence of degradation on the machine. They passed their outage. So they're now running almost on their 7th year at the time of the recording of this training. So they're very happy with their compressor. It went from keeping them up at nights to being a solid performer for the facility. Now that same customer, when they were considering putting halos in, they were worried, as everyone would be, of being serial number one, right? They had a risk reward situation. They were ready to go because they had a compressor they needed to do something with. They were going to take it out and replace it. They said, well, we'll give it one more shot. But they did ask ATGI to try to fail the seal. They wanted under a test, conditions to fail a halo, and they wanted to see what would happen if we failed it. So they asked them to set up a test rig, and they built an arbor with, it was supposed to be 3/1000 or 3 mils eccentricity. That's 0.003 inches of eccentricity on the arbor. The machinist actually reread the print wrong. They made it 6 mils, and they just went ahead with that anyways. They then built the test rig so that the arbor and the halo seal itself could be offset during operation, so they could just tighten the bolt, and then the seal housing would slide over 10/1000. Now they ran this to a concentric arbor. They got a baseline for the leakage. Then they put the eccentric arbor in and measured the same exact leakage. Then they offset the 10/1000 during the test, and the leakage did increase a little bit, but it didn't increase, excessively. This was a controlled increase. They took that offset back away. They dialed it back to being in line with each other, and the flow returned to the amount of the 6 mils eccentricity, which was the same as the concentric arbor. So they tore that machine apart. They tore it apart. They expected to see the seal rub and to have made contact with that much of offset, and it didn't. Okay, they didn't rub at all, and the performance passed with no change. So they were very happy with that. We've got 2 videos to show you of Halo Seal in operation. The first one here shows a 6-pound differential on a gauge. They're going to build this up to 6 pounds, and they're going to activate and deactivate the seal so you can see what that looks like. And what you're looking at is the downstream side, the low pressure side of this. There's some cutouts here where you can see the seal, spring. This is that fixed ring, the spring and the pads, and they just deactivated. This is an arbor and it's stationary. Okay, so this is just a test showing how the seal activates and deactivates with an excessive amount of motion here. This is more motion than you see in a typical install. They made it this way for the video, just so that it's easier to see how the pads are activating and deactivating, and how much motion you can really get out of a halo seal. The second video shows that arbor running, and this is a very eccentric 79 mils of eccentricity on this arbor, but the halo was built with a concentric design, so you can almost see that those two circles aren't the same radius, and you can see that the pad is staying active. As long as there's gas flowing underneath that pad, it will create that negative static pressure like I explained earlier, and it'll draw the pads down to the rotor until the forces are balanced. So they show, I don't know why, but they show all four sides of the seal operating, but they're all the same exact pad, the same length. So this is our product unit experience list. I would love for this list to be 3 times its length, but it isn't. That first customer that did this special testing, that had the machine that was having a hardship of operating, was installed in August of 2012, and there it is, serial number 1. Dresser-Rand and Siemens purchased the intellectual property to the halo seals, and we have installed it twice in new equipment. This is new equipment 1A and 1B. This was the same customer, same time, and we put it in the datum frame 4 compressors. One for a booster gas and one for a gas lift. Now, those machines were installed in the Gulf of Mexico. They have had intermittent operation on the gas lift, but of the 2 trains, so there's 4 units total. We did factory test both of them. They've had differing hours of operation, but fairly successful to date. In our aftermarket, we first sold it to a propane refrigeration compressor. This was a Legacy 745B, a fairly large machine. I think these were like 24-inch seals, and it was a low horsepower unit. But this has been operating. This is our longest aftermarket job and most experience. It was installed in June of 2015. Now, prior to this change, that machine had operated for 17 years without being torn down. So we certainly would love to see what those seals look like, but it's going to be another 12 years before we get that chance, because it's running rock solid for them. Then we did a methanol compressor, and this was a severe erosion situation where some sand and some slag had been run through the machine and tore the aluminum labies all the way out. It was completely, they were just eroded to the point of almost failing, and we turned to halos to be the most, it's the strongest material. It's Inconel, so it certainly is going to stand up to that erosion. And then the last is for an injection machine. It's a 463B, a very high horsepower machine. The hydraulic efficiency, hydraulic performance was the primary goal. CO2 reduction, that is the goal of this installation of halos. They just started in October of 2018 and just passed their 6,000 hours of operation mark. Again, very satisfied to date with the halo seals. Now, I'm going to include with this a brief narrative. This is just how we got involved in each of these halo installations, whether it be aftermarket or new equipment, and it's just there for your own reading purposes and a little bit of background. The only thing I will mention is that this does not include the history in terms of gas turbines, which we have quite a bit of experience now with the gas turbine stuff, some experience with steam turbines, and then our developmenting testing that we did at Siemens as well. It doesn't speak to our experience there. We left those out. We're just mainly talking about industry and customer experience. Now, there are some papers, and if you write to me or contact your, local Halo representative, whoever those are. There are some papers available for additional reading, and we presented that first new equipment project. We presented that at the Turbo Symposium. So if you're still listening, my name is Gregory Lynn. I put emerging technology here. At the time that I got involved with Halo Seals, I was the business development manager for the aftermarket. I've worked primarily in the Dresser-Rand Olean, New York office for my entire career. I started in 1991, and I worked in many of the areas inside this factory, from design, development to testing. But I made my home in marketing and in sales, so I work with the Mods and Ups groups now. Also, I should mention that Jeff Wurst is now taking a position as the Halo product manager, and both our contact information is there. And if you'd like a quote, you can also write to our Turbo Revamp and Upgrade request email inbox. Thank you for your time, and I hope to be talking to you shortly.